Alright, we're going to take a look at section 2.2, which is inductive and deductive reasoning. We're going to take a look at these two types of reasoning specifically today, and to help get us started, let's take a look at these vocabulary terms. As I scroll down, let's take a look at our first core concept right here, which is inductive reasoning. And so the first term I have highlighted in pink is conjecture. A conjecture is an unproven statement that is based on observations. When you think of an observation, it is something that you see. Okay, so that is one of the main differences between when we use inductive reasoning and deductive reasoning is that we do come up with the conjecture, something that you see. So to continue on, the sentence, it says, you use inductive reasoning when you find a pattern in specific cases, and then write a conjecture for the general case. So for example, what you may see in your homework is you see a set of numbers, like 2, 4, 6, 8. All right, you can make a conjecture that the next number will hopefully be 10, because hopefully you realize that each number has increased by 2. So that is something that you base on observation, and you can go ahead and come up with that end result of 10 based off of the pattern that you see there. Okay. Next up, we have a counterexample. This is to show that a conjecture is true, you must show that it's true for all cases. So that right there is important. It must be true every single time. All right. If you can find a counterexample, which is an example that'll make it false, then everything that you said is true, even though you say you have 10 examples of something being true. That one example that's false just throws everything out the window. Okay, so for example right here, I can go ahead and say for my conjecture, all prime numbers are odd. Okay, so if you think about your prime numbers, remember, it can only be divided by 1 and itself. So if you think, all right, maybe 7, prime number. Okay. What are some others that you could possibly think of? 11. All right. So there's 7 is odd, 11 is odd. We can say 17, 19. Right. Those are all prime numbers. But there is one that we can counter or find a counterexample of that will discredit everything. And if you think about it, it is going to be the number 2. 2 is prime and even. So it just takes one counterexample right here, and that's the specific case that makes the conjecture false. We could talk about another conjecture that I could have right here would be all quadrilaterals are rectangles. Okay, well, that is true. A quadrilateral is a rectangle, but a counterexample to that would be a quadrilateral, for example, that's a square. Right? A square is not a rectangle. Or let's say a quadrilateral that is a trapezoid. All right? So that would be a counterexample to that. Our next reasoning right here is deductive reasoning. Deductive reasoning uses facts, definitions, accepted properties, and laws of logic to form a logical argument. Laws of logic are some of the terms that we may have used before. Okay, and it says this is different from inductive reasoning, which uses specific examples and patterns to form a conjecture. So don't forget, inductive reasoning, examples, patterns, things that you see. Deductive reasoning uses facts, all right? Properties that we've gone over, definitions. That's why it's so important that in chapter 1 we learned so many different terms, and we're going to have to keep using those terms to come up with a logical explanation to prove certain things are correct. So as we move down right here, let's take a look at laws of logic. We have two specific laws of logic. The first one right here, let's take a look at, is law of detachment. The way law of detachment works is as if the hypothesis of a conditional statement is true, then the conclusion is true. All right. So we could say that the interior angles of a triangle is 180 degrees. Okay. Or if the interior angles of a polygon is 180, then the polygon is a triangle. So that right there would be something of a true conditional statement. Okay, it is true all the time. There is no ifs, ands, or buts about that. Okay, let's take a look at the law of syllogism. Okay, now the law of syllogism is like a three-part system. You can see right here, it says if the hypothesis P, then Q. Then we have Q, then R. If these two statements are true, then what we can make is a connection between P and R. A simple example that I'll try to give you right here is this. If I bought this phone in, let's say, year 2010, then it is older than this tablet here that I bought in 2013. Okay, so this would be P, this would be Q. So then I start off with Q again, and I'll say that if I bought this tablet in 2013, then it is older than this phone that I bought in 2015. Okay, so now we have three items here. Okay, so with these three items, we got, remember, this right here phone was older than the tablet as opposed to this phone. So lastly, we can conclude that if I bought this phone right here in 2010, then it is older than this phone, which was bought in 2015. And that's the conclusion. We make a connection between three different things. Okay, we have once again 1, 2, 3, and then in the end, we can go ahead and make a connection between the first and the last. And that right there is the law of syllogism. All right, so let's take a look at some examples to help you understand or see if you understand the concepts that we just talked about. The first one right here says describe the pattern and then write or draw the next two numbers. So I'm looking right here, 20, 19, 17, 14, 10. What's going on? Okay, what is going on? Now, if you look at this, I'm trying to find, with the set of numbers, hopefully, we have ourselves a pattern. And remember, right here, we're going to be using inductive reasoning. Right, we're looking at patterns. So I'm looking right here, I got -1, -2, -3, -4. So I can think it's safe to say that the next term would be, we subtract 5 from 10, and that would be 5. If I subtract, okay, so we have 5 right here. If I subtract, next up would be 6, then 5 minus 6 would get us -1. So this right here are the next two numbers. All right, number 2. I see two things going on. I see numbers like 2, 3, 5, 7, 11, and then hopefully you see that the signs are changing. Well, what kind of numbers are 2, 3, 5, 7, and 11? These numbers right here we could say that they are prime. These are prime numbers, and the signs are alternating, meaning that they are changing from positive to negative, positive, negative, positive, negative. So if this is -7, this is 11, then the next number should be negative. The next prime number happens to be -13. After that, the next number should be positive, and the next prime number that's positive is 17. All right, let's move on to number 3. We got CEGIK. What's going on here? We have right here, these are letters of the alphabet, and then every other letter is skipped, okay? And we have M, and then O. All right, and then number 4, hopefully you see what the pattern is each and every time another smaller rectangle or square is being drawn. All right, so we go from 1, 2, and then let's go ahead, we'll have 3 right here, and another one will be where we have 4 little squares inside of the square. Okay, let's move on. All right, this is where things get a little more complicated. This is where we have to make and test a conjecture about a given quantity. So what we're trying to do right here is make sure that we can prove that the statement, for example, number 5, the sum of 2 negative integers, we can go ahead and show, make an example of that or show that. All right, so let's go ahead. Sum of 2 negative integers. Remember, there's infinite number of negative integers. We can make it simple. I can go ahead right here. The sum of 2 negative integers, I say -5 plus -3. Okay, and that right there is equal to -8. All right, there you go. Sum of 2 negative integers. I took 2 negative integers, I added them up because that is the sum, and we have -8. Next up, number 6, the product of 3 consecutive non-zero integers. Now remember, the product means to multiply. So we're trying to multiply 3 consecutive non-zero integers. And remember, consecutive means one right after the other. Okay? You may have heard teams winning consecutive years because they have won back-to-back championships. Or they can right now win back-to-back-to-back championships. All right? So we take 3 non-consecutive zero integers. Let's make it easy. 2 times 3 times 4. And that would be equal to 24. All right, next up, number 7. Now we're going to try to find a counterexample that shows that the conjecture is false. So we're trying to figure out can we make whatever that they're showing right here false, the statement. So it says if m is a rational number, then n squared is always less than n. If something is a rational number, it is a number that can be divisible, and you get nice whole outcomes. All right. Don't forget, also rational numbers would be fractions. So let's think right here. If n is a rational number, then n squared is always going to be less than n. The example I'm going to give right here is let's say, for example, we have 3 halves. Okay? So if I have 3 halves right here, let's say this is n, and I square it, it's saying that it's supposed to be less than 3 halves. Okay? That's the statement. It's saying that's supposed to be less than this. So n squared is less than n is what's being told. Well, I'm showing you right here that if I have 3 over 2 and I square that, is that going to be less than 3 halves? Well, if I take 3 over 2 and you square it, and remember the exponent goes to both top and bottom when it comes to a fraction like this, I'll end up with 9 over 4. Is that less than 3 halves? Or sorry, it's saying that it's always less than n. So yeah, once again right here, if I look at that, that's 9 over 4, and that is always less than n. Is that the case right here? So if we go ahead and continue on, if I take 9 divided by 4, 4 goes into 9 2 times and then 1/4. If I take 3 and divide it by 2, that's only 1 and 1/2. So it's safe to say that right here, I just made myself a conjecture or a counterexample, because this is not the case, right? 9/4 is greater than 3 halves. All right, so that would be, I right here just made a counterexample by using a fraction or a rational number. Let's take a look at number 8, which says line K intersects plane P at point Q on the plane, and plane P is perpendicular to line K. Well, I think that could be pretty easy. Let's go ahead, I'll draw myself a plane right here. This is plane P. And plane P is perpendicular to line K. Well, if I'm going to make a counter example, I'll go ahead right here, make line K right here going a little sideways, right? I'll have it going diagonally. It intersects right here at a point Q. Well, it's not perpendicular. There's our counter example. All right, next up, let's go to law of detachment. Now, once again, law of detachment is about, right here, it says that if the hypothesis of a conditional statement is true, then the conclusion is also true. So number 9 states this: if a triangle has equal side lengths, then each interior angle is 60 degrees. Triangle ABC has equal side lengths. Okay. So what we can conclude right here is that based off of this statement, if a triangle has equal side lengths, then each interior angle is 60 degrees. This triangle ABCD or ABC has equal side lengths. What we can conclude right here is that each angle measure of triangle ABCD or ABC is 60 degrees. So part of the understanding here is this: if I have a triangle and they're saying that all sides are congruent, in order for all these sides to be congruent, all the angles must be congruent. And we'll talk more about this later on when we get into details about triangles, but then all of these angles are 60 degrees. And the interior angles of a triangle happen to be, the sum of the interior angles is 180, which ends up working out right here. Let's go to number 10. If a quadrilateral is a rhombus, then its pair of opposite sides, then two pairs of opposite sides are parallel. Quadrilateral PQRS has two pairs of opposite sides that are parallel. Now remember, when we use law of detachment, we have to think, right? If the conditional statement is true, then the conclusion is true, and it must be true for all times. Okay? You cannot come up with a counterexample right here. So the thing is, you remember earlier we talked about quadrilaterals, and I said like if the quadrilateral is a rectangle, if it has four sides, then it's a rectangle. Well, it's not always the case because we could say a quadrilateral is also a square. So if you remember that right here, quadrilateral PQRS has two pairs of opposite sides that are parallel. It could be a square, it could be a rectangle. Those are all quadrilaterals that still have opposite sides that are parallel as well. So in this one, we could say that it is, if is it possible? No, this is not possible. The reason being, it's not always true. I'll give my counterexample. The quadrilateral can be a square or a rectangle. All right. Let's take a look next at number 11. You go to law of syllogism. It says, use the law of syllogism to write a new conditional statement that follows the pairs of true statements, if possible. All right, so looking at number 11. Remember, you start right here. We have the first hypothesis. We'll say, if it does not rain, that is P, then I will walk to school, that is Q. If I walk to school, see, remember, the conclusion will now be the hypothesis, so I'll put Q right here, and then I will wear my walking shoes, which is statement R. So once again, if it does not rain, then I will walk to school. If I walk to school, then I will wear walking shoes. We make the connection right here at the end, and then we go to P, remember, implying to R. And so what I can say right here is this: if it does not rain, then I will wear my walking shoes. You don't want to wear nice fancy shoes when it's raining, right? You don't want to mess them up. I know I don't. So I'll wear some beaters, right? Let's take a look next up at number 12. Let's see if we can come up with our statement here using law of syllogism. So if x is greater than 1, that'll be my hypothesis. So let's go ahead and put right here P. Then 3x is greater than 3. There we have Q. If 3x is greater than 3, right there once again we have Q. And this right here will be statement R. Then 3x quantity squared is greater than 9. So finally, we connect all the things together. Remember, it goes from P to R. And so I can say that if x is greater than 1, then 3x quantity squared is greater than 9. All right, and there is the law of syllogism. Now, oftentimes you may see questions where they don't have things actually written in this same order, where it goes from P to Q, Q to R. It's not that nice. Sometimes what they'll do is you'll have to read the statements carefully, because it still might have law of syllogism implied, because you may see, for example, like they could put 3x is greater than 3, then x is greater than 1. And they could write the second sentence as is. Well, hopefully you'll realize that that 3x is greater than 3 appears 2 times. And if it appears 2 times, that would be your Q statement, even though it wasn't written in that same exact order. So if you could figure out that, hey, I see in the statement that maybe Q is written twice, or I see a statement part of it written twice, that would be Q, and you would be using the law of syllogism. All right, so that concludes section 2.2.